Hello everyone, my name is Samir Mukita. I am a graduate student at the Georgia Tech College of Computing in the Online Masters of Science and Computer Science program, and I am enrolled in the Introduction to Cyber-Physical System Security Spring 2020 semester, and I'm here to present on smart maintenance via dynamic fault tree analysis, a case study on the Singapore MRT system. This work is based off of a paper originally presented at the 2017 47th Annual IEEE IFIP International Conference on Dependable Systems and Networks by researchers from the Advanced Digital Science Center in Singapore, as well as the University of Illinois at Urbana-Champaign in Illinois, United States. So we're going to be talking about fault tree modeling, which essentially is a methodology that's used in reliability engineering and other risk assessment practices. And we're going to apply computer algorithms to see how that can be done more efficiently. And a prime example that we're going to be using to study this methodology is transportation system, which is the Singapore Metro. And so here pictured, we have the Ion Orchard station in Singapore. And as I'll come to introduce to you in the first section, we're going to talk about a little bit more about the transit system itself and the implications for this type of analysis. We're going to talk about the fault tree analysis itself, the fact that there are several types of or subtypes of this type of analysis. There's a standard and a dynamic methodology. Then we're going to apply this methodology to our model system, which is the Singapore Metro. We're going to apply this fault tree modeling to characterize it in a variety of experiments to infer some indication of reliability. These results are going to be presented, and we're also going to discuss some of the implications within this application and other industries. And then, of course, this sort of methodology is extended to other related work that can be used to infer the reliability of systems and using cyber physical components. So let's talk about the Singapore MRT again. Another close-up of the Ion Orchard metro station. It's one of the heaviest urban rail systems in the world, and it's got a tremendous ridership of 3 million people. And like I had mentioned before in the previous slide, this is an example of a massive cyber-physical system, which is the topic of study in our course. And a disruption to this system would cause a great impact. So what sort of impact are we looking at here? Well, it's governed by the design, which is very complex. Why is it complex? It uses a lot of commercial off-the-shelf components. And so maintenance is done at a individual component level. But what this paper tries to analyze is if this can be done in a more efficient way. And this confers other advantages as well, too. But if we can look, instead of doing maintenance per individual component recommendations that are usually vendor specified, if we look at whole systems, we can perform maintenance in a much more efficient manner that perhaps we confer a reliability advantage or some other advantage that is perhaps driven by data. And so one methodology which we can use to quantify reliability, and we're going to be talking about ways to do this specifically, is by using the fault tree analysis methodology. So what is fault tree analysis? This is a fundamental technique that permits reliability, availability, maintenance, and safety analysis in complex systems. It's data-driven. So we're going to be using this methodology to apply numerical algorithms in order for us to quantify first the basic events that comprise the system and then their tendency or probabilities to fail. And as you can imagine, this can be used to predict future events, to be proactive, and to be more efficient. And there are several ways of accomplishing this. And obviously, for a complex system, you may need to apply a more dynamic approach to your modeling methodology, which is this dynamic fault tree approach, which is what we're going to be using in this talk. And as I've mentioned here, it considers the sequentiality of events, whereas a standard fault tree, and we'll go through this in more depth, does not consider that. So when we use this methodology to model, we essentially use a system map that is comprised of logical gates, and these gates show the relationship between the components and basic events. Similar to a standard fault tree, we would have the AND and OR gates, which are pretty self-explanatory. We have a voting gate, which will fail if k out of n total inputs fail. We have the PAND gate, which is a great illustration of how dynamic fault trees differ from their standard equivalents. The PAND gate output will fail if inputs fail going from left to right, but not right to left. So this is an important distinction of the dynamic methodology. And we'll talk about how this changes the modeling of our system. We also have, in many cases, spare or redundant components, and in the DFT modeling methodology, this also is illustrated a bit more clear. And we also have the ability to show dependence on other events using the dynamic fault tree methodology. And so like I'd mentioned, common use of DFT is when there are redundant components or subsystems, and spare components is another way to put that. And in a DFT model of an exclusive spare, you can see that we can infer which component is the spare and which component is the sort of permanent installation when the entire subsystem fails. And you can see that the spare components are grouped under a shared OR gate, and this is fairly typical for modeling entire systems or subsystems, that there will be a tree of components or subsystems, subassemblies existing under a much larger OR gate. And this will apply to our test model as well too, that we'll discuss in a little bit. And you can see on the right, the standard fault tree model, you can't really infer unless they're labeled explicitly which component is the spare and which one is the permanent installation. The redundancy can be inferred, but not much more than that. So this is why we use the dynamic fault tree model, because exclusive spares are essentially represented by AND gates in the standard methodology, and that can be extremely limiting. So another instance where the standard fault tree model is limiting is when there are shared spares. And so in the dynamic model, we actually can show which or how the spares are shared. And in the standard fault tree model, it's simply represented as a voting gate. So at this point, it's fairly clear that the standard fault tree model is fairly limiting in how we study the system, especially one as complex as a heavy urban rail system. So we're going to be using the dynamic fault tree method. This will permit us to do two things with regards to studying our model system, which is the Singapore Metro. There's a qualitative analysis component, which is finding the minimal cut set of low-level failures causing the top-level failure. And think of this more as of a way of finding dependencies on different components and events. There's also quantitative analysis that will occur, and we'll be computing the overall system reliability, which essentially is the mean time to failure of the system. And with one, we can do the other. but they both have advantages to study independently as well. But in order to do this first, we need to have a good description of the system in order for us to build the model. But before we do that, rather before the authors of the aforementioned paper did that, they actually took a survey of the major historical incidents impacting the service on the train. And this was to better understand what had previously caused issues. On the left, you can see the causes, and you can see a majority of them were related to signaling components at 46%, and a close second at 42% related to the rolling stock subsystem, which equates to the train vehicle. We'll be talking about how to characterize the different systems and components in the train in the next slide. So on the right, you can actually see the impact to commuters, and clearly anything that had to do with power imposed the most amount of fines, caused the greatest delays, and impacted the most customers. We couldn't talk about Singapore without talking about some fines. So this is finally where we're going to start to look at how we better understand the individual components and subsystems making up the metro so that we can construct our model. And the main system model is composed of 3 subsystems. There's the traction power subsystem, or TPSS. There's the rolling stock subsystem, or RSSS. And then there's the train communication subsystem, or TCSS. And a better way to think about all of these is the TPSS represents the track, or the power infrastructure. The rolling stock subsystem, think of it like the train vehicle or the car. The controls associated communicating with the track and controlling the speed and train movements thereafter. And then finally, the link is inferred by the train communication subsystem. Any component in between that relays communications between power, the rolling stock subsystem, and other miscellaneous signaling components between stations, operators, and such. So let's take a closer look at the TPSS. We're going to look at component topology to better understand how we construct a DFT model. And essentially, there's a power source that's coming from the common municipal utility, and there will also be a backup source as well. Now, this power is fed to the rails and controlled by circuit breakers. And these circuit breakers are arranged in redundant groups. And here's where we can start to apply the DFT model to get a better understanding of the relationship of the components. So we have 2 circuit breaker groups with a shared circuit breaker, redundant component. And so, and then that's represented on the left here of the DFT tree. And on the right of the DFT tree, you can see that there's a primary power source and a backup power source as well too, which is used as a spare. And then failure in any one of these power components would cause a failure of the overall traction power subsystem. So whether it be a failure in one of the circuit breaker units, or if the power source also goes down. But keep in mind that there's a lot of redundancy built in here. There are spare circuit breakers, and there are also spare power sources. So the traction power system, from a reliability standpoint, appears to be fairly robust, and the numbers which we will receive through our computation will indicate as such as well. The next subsystem which we'll be discussing is the rolling stock subsystem. This is referred to the operation system that's deployed on the track. It draws power from the power subsystem, and it's controlled by signaling for operation. So we actually are going to distinguish these two separate subsystems, control flow and power flow. And so on the train, to discuss the power flow, there are two motor cars on each head, and each motor consists of two bogies. To ensure normal operation, at most one of the four bogies is allowed to fail. Each bogie has two power collecting shoes that get power from the third rail. If one shoe fails, the train can still operate normally. It's designed for redundancy. But if two shoes are damaged at the same time, the car would not be able to draw any power from the third rail. And the train may still operate, but in a degraded mode with reduced speed, or it may stop entirely. And these PFD or power flow devices are shared by bogies, so they're used for transmitting the power. In addition, this PFD3 links the movements of the car to the control flow subsystem, which is receiving commands from this ATC or automatic train unit. And these units reside both trackside and on the train. It's used for accelerating, decelerating, braking, etc. And these ATCs are actually part of the communication system, which we'll discuss next. So you're already starting to see the interdependence between subsystems, but we do apply a DFT model exclusively for the RSSS to understand propulsion control, or specifically a failure in propulsion control. And that would look like a failure in some of these, again, redundant components. You're seeing a lot of AND gates, nested AND gates here amongst both the signaling components, the ATC control component, the power flow devices, so on and so forth. The next and final subsystem which we're going to discuss is the train communication subsystem, or TCSS. And this one's a bit easier to understand. This includes all of the communications and link equipment between the vehicle and the track, and both of those components to operations, personnel, to users, to operators, controllers who monitor the whole thing as well. And for a lot of these critical transportation specific components, not necessarily the monitoring ones, but the critical transportation ones, there's a degree of redundancy that's built in to the actual data link itself. And that's to ensure integrity across while, for example, something is in movement, and parameters such as speed may change. So a consensus logic is actually applied such that, in some components there has to be an agreement of two or majority stake of, for example, transmitted packets, for instance. So the TCSS comprises 24 basic events with 5 spare gates, 1 voting gate, 2 AND gates, and 7 OR gates, which is quite a bit of OR gates considering the low-level topology. And failures in this subsystem can be caused by defects in communication media, defect in track equipment, faults in wireless networks, or failures in the central server. So now that we've got the whole system sort of modeled out, we're going to conduct some experiments using computation on this integrated DFT model. And for the whole system, it was 70 basic events connected over 9 spares, 4 functional dependents, 2 voting gates, 13 AND gates, and 21 OR gates. Now, this is a limited model as well, too, as explained by the authors of the paper. Due to computational difficulties, only single instances of the TCSS, the RSSS, and the TPSS were introduced to the computation, whereas in more practical or real life scenarios, there would be multiple instances each. For example, multiple trains running simultaneously on the same track. But due to computational difficulties, that was not introduced. Another limitation of this work actually is modeling failures of software. And while the authors go on to acknowledge that software failures happen more often than hardware failures, predicting or modeling their exact frequency and the nature of the failures is very difficult. And so for the purpose of this computation to study reliability, we're actually not including software failures as components in the larger model. But the two experiments that we want to do is calculate the minimum cut set. And this is going to represent the minimal set of component failures that cause an entire system failure. This is done using a top-down algorithm which expands downwards until basic events are reached in this dynamic fault tree model. And when broken down, this data is fed into a variety of software tools, including this DFT Calc, which was used by the authors of the paper, which quantifies reliability. The web version of the DFT Calc tool was used by the authors of this paper, and it takes the models that we've described in the previous sections in a format called Galileo, which we'll talk about in a little bit. And it's going to basically calculate the probability of failure as a function over time. And the DFT data is fed into this tool, broken down event by event, component by component. And when we look at the qualitative analysis that's done to find the minimum cut set, there were 5 single point failures that were found. And you can see the number 1 is the wireless communications media. Redundancy is present, but the coverage is unknown. That's sort of a limitation in the study in general, but the top-down algorithm by Professor Dugan from the University of Virginia was used, and we're going to be discussing her contributions to the field of reliability engineering as an extension to this in a few slides. And while the traction control subsystem uses a single high reliability media for wireless communications, failure of this media brings the whole system down or cause it to operate in a greatly degraded mode. So we can see immediately the importance of the communication subsystem. And the results from the DFT Calc run indicate that as well. You can see that the train communication subsystem has a drastically lower mean time to failure compared to the other subsystems. The train power subsystem is 8 years, and the rolling stock subsystem is half a year. But the communication system is a mere 21 days. And as this bottleneck or limiting subsystem, the mean time to failure of the entire train service converges on that TCSS value. The output of the DFT Calc tool is shown here. Now pay attention to the legend, specifically the unit divisions for the specific curves. You can see the train service and the communication subsystem are divided in 100 hours, whereas the power subsystem and the rolling stock subsystem are divided into 10,000 and 1,000 hours respectively. Nevertheless, on those base 10 scales, you can still see that the overall trend follows the blue curve, which is the communication subsystem, and at a much overall lower failure probability, you have the power subsystem, inferred by that high degree of redundancy that we saw in the DFT model earlier. And so we'll discuss some of the results. Overall, the train system is the most vulnerable to failures in the signaling system. That was evident from our qualitative analysis, looking at the minimum cut set and the single point failures, and also from results from DFT Calc. The mean time to failure value for the whole system model is very close to that of the signaling system. And what this means is that the cyber components are the bottlenecks in building a highly reliable train system. And frequent, thorough testing, maintenance of the communication system is highly recommended. And this highlights the criticality of the sensors, the networks, the network components that these sensors communicate on, and also the integrity of the communications protocols, as we're coming to study in this course. And so as extension to this work, I wanted to discuss some applications of this. There are intelligent sensors available commercially, which assist in process development as well as commercial deployment. They adapt to process conditions, and they offer real-time diagnostic capabilities simultaneous to measurement. And clearly, as we've seen in this scenario, something like this implemented throughout a variety of process control scenarios would infer a lower degree of maintenance requirements, or maintenance that can be handled a bit more intelligently than at predefined intervals. And you could also use the output of the diagnostic data to perhaps perform similar calculations that we saw in previous slides to confer an even smarter advantage to your maintenance strategy. Mettler Toledo is an example of a vendor that provides this capabilities in their iSense line of process analytics sensors and transmitters, which offer this intelligent sensor management technology. So I mentioned previously that this DFT Calc tool takes in the DFT model data in a format of Galileo, and this is actually another more well-known software platform that's in production use. It was created by researchers at the University of Virginia, embodying the work of Dr. Joanne Bekta-Dugan. Dr. Dugan's algorithm for MCS computation was actually used in the paper that I'm describing today. As I mentioned, it's another software tool used for both reliability analysis and probabilistic risk assessment, and it's in production use by none other than NASA, and I'm told other high-stakes reliability engineering endeavors. DFT can also be used to identify vulnerabilities, and so we have to understand that this risk assessment techniques and computation can be used for both offense and defense. But clearly the best strategy to prevention is at the physical level. And you can see this is an awareness poster actually from the Singapore Metro showing what looks to be a passenger reporting a pineapple device hanging out in the metro. And this again indicates the importance of that communications link, and that importance is well known to attackers. The authors go on to describe additional related work, which includes the failure mode and effects analysis methodology, or FMEA. This is one of the first and still more popular methodologies that's used. It's a technique that's used in safety critical industries, any industry that requires a very thorough analysis of individual components and subsystems. And the output of this analysis can be useful in constructing fault trees. So conducting this analysis as requisite or simultaneous to DFT analysis can be very useful. There's a variant of this analysis that includes a vulnerability assessment so FMVEA. And here's an example of an FMEA template. There are many organizations that provide quality tools and templates that allow engineers to conduct this assessment. It's very useful. We also have a relationship to the time fault tree. Similar to the dynamic fault tree, there is sequentiality, but the time fault tree is more specific in the sense that it adds known time delays to the basic events and gates of the fault trees. And this allows us to calculate things like urgency and the time between fault and accident more accurately. And in safety critical implementations of these analysis techniques, that can mean life or death. I want to thank you very much for your time. I'm a student studying computer science at Georgia Tech. If you have any questions for me or would like to get in touch, my email is below.